Hello everyone and welcome. Today we're going to discuss about online two-dimensional load balancing. It's a joint work with Sungjin and Debmalya. The motivation to this work comes from the world of cloud computing and virtual machine placement, where we need to assign jobs to servers, and we model it in the following way. Each job is a multi-resource requirement. A job might require a different amount of CPU, memory, etc. And we model it simply by giving a different dimension for each resource. And this naturally yields the following problem of vector load balancing. In vector load balancing, our goal is to assign jobs of m identical machines, where each job is a d-dimensional vector. Let's see an example with a three-dimensional vector. Here we have a set of 5 jobs, and our goal is to assign it to a three-dimensional bin. Here's an example to an assignment, and the goal is to minimize the max span, the maximum loaded coordinate in any machine. In this talk, we're going to focus on the online version of the problem, where there is a sequence of vectors. The vectors arrive one after the other, and the algorithm must immediately and irrevocably assign the next vector to a machine. One famous example is a greedy algorithm, which is simply assigned to the machine, which minimizes the maximum load. Let's see an example. So the first vector arrives, it's got assigned. The second vector is the third vector. The fourth vector, note that assigning it to the first bin will minimize the maximum load. And now the next vector arrives, and in this case, assigning it to the second bin will minimize the maximum load. So this is a greedy algorithm. Obviously, this won't yield the optimal assignment. So in order to analyze the performance of an algorithm, we use the well-known term of competitive ratio, where we compare the objective function, in this case, the max span of the algorithm versus the optimal objective function. The optimal max span, here in the example, we can see what the online assignment and the optimal assignment, and our goal is to bound the ratio between them. And if we are able to bound this ratio for alpha for any instance, we say that the algorithm is alpha competitive. So there is a lot of work for vector load balancing for two special and interesting case. First, the one-dimensional case. It's also called the least scheduling or minimizing the max span. For this, there are a set of results. The best known result for the case of unknown opt is 1.916 by Albert. And for the non-opt case, the best known result is 1.5. But for both cases, there is a lot of literature about it. And the other interesting case is what happened for the general D, where the number of dimension is more than 1 and can be arbitrarily large. And here there are tight result up to a constant factor of log D over log D. And again, there was a lot of work what happened when the number of dimensions is large. Okay, so, but unfortunately, in practice, the number of dimensions is usually small. So, of course, we can use the d-dimensional vectors, but it won't guarantee, because of the constant factor, it won't guarantee anything interesting about the problem. So, in fact, the majority of system scheduling just consider 2 resources, the memory and CPU, and we cannot use the current result in order to understand this problem better. And this work is trying to understand what happened for the interesting and practical case when the number of dimensions is small, 2 or 3. Let's start. We'll focus on when the number of dimensions is 2. So in order to understand how much we don't know until this paper, let's start with the analysis of the greedy algorithm where D equal to. So the only thing it was known that the greedy competitive ratio is less than 3. Let's see a quick proof. This proof will help us to understand how to improve this competitive ratio guarantees. So the proof, so first I'm going to normalize op to be 1. That means that the average load in any dimension is at most 1. And second, all the vector coordinates are smaller than 1. So assume for contradiction that after I assign the last vector, the maximum load is more than 3. Because the vector is smaller than 1 in any coordinate, that means that every machine has a dimension of at least 2. Otherwise, the greedy will choose a different machine. That means that the total load in any machine is at least 2. And by the pigeon principle, some dimension has a load of at least m. That means the average load is more than 1, a contradiction to the fact that O equal to 1. So this is the proof was the only thing that was known about vector scheduling for small number when the number of dimension is 2. So the first question that we need to ask whether this analysis is tight. So on one end, it's looked like the analysis is tight. If we reach to a state that we have m/2 machine that have a load of almost 2 in the first coordinate and load of 0 in the second coordinate, and the other half of the machine has a load of 0 in this first coordinate and load of almost 2 in the second coordinate, then if the next vector is 1, 1, then anywhere that I will assign this vector, I will reach to a load of almost 3. And that means that the competitive ratio guarantee is 3. Not that we don't overflow the volume constraint in this case. So in order to understand whether 3 is a correct answer, we need to understand whether this state that we have, this unbalanced state that we have m/2 machine with a lot of load in the first coordinate and 0 load in the second coordinate, and its mirror on the other half of the machine is possible using the greedy assignment. Okay, so the first question that we need to ask, whether can we reach to this unbalanced state. So answering this question for arbitrary number of machines, it's maybe hard. So let's start with an easier question. For m equal 2, are these following states are reachable using the greedy assignment? First, that we have 2 and 0 and its mirror point. So it's easy to convince that this state is unreachable, but now I can ask whether I can reach to this state when in the first machine, the first coordinate is 1.8 and the second coordinate in 0.2, and the second machine is its mirror 0.2 in the first coordinate and 1.8 in the second coordinate. And of course, I can continue and try to understand what's a reachable space. So actually, in this work, we first analyze not just the competitive ratio, not just understanding what happened to the algorithm using the last assignment, but we analyze the entire reachable space of the algorithm, and using it, we achieve to a tight result. So just in a few words, in order to bound the 4-dimensional space, we have 2 machines with 2 coordinates each. We find some covering body that's covering this reachable space, and we prove a closure property under greedy assignment. I will explain it maybe into more details later, but more important, we give a complete characterization on the reachable space of the greedy assignment. And we can present it here. So I cannot present a 4-dimensional body, but if I set the first machine to be, for example, 0.2 and 1.8 as in this animation, so the red zone represents the unreachable space, and the white zone represents the reachable space. So it's easy to see that 1.8 and 0.2, its mirror point is not in the reachable zone, suggesting that the competitive ratio might be better than 2.8. If I check the point 0.4 and 1.6, if the first machine load is 0.4 and 1.6, then its mirror point is inside the reachable, suggesting that the competitive ratio might be worse than 1.6. And in fact, the boundary point for the greedy in the symmetrical case is 1/3 in 5/3, suggesting that the right bound is actually 8/3. Okay, so before I will present our result, I will first introduce our approach for small dimension. Is first to reduce a problem for arbitrary number of machines to a small number of machines. And then we characterize the reachable space of the algorithm, and using some properties that we prove, we show a lot of interesting results. Okay, so we reduce, the first and important step is to reduce the number of dimensions. Using this approach, we are able to show that greedy is indeed 8/3 competitive. And using this approach, we are able to analyze not just a greedy algorithm, but a large family of algorithms that we call priority-based algorithm. I will soon give you the definition. And one example of a priority-based algorithm is a best fit, as we define it. And for the non-opt, we saw that we can improve the competitive ratio to 2.25. We also use this scheme to analyze the first fit, specifically to show that first fit for the cases for the non-opt is 2.5. Okay, so we use our scheme in order to analyze all this priority-based algorithm. And moreover, we show how to extend this approach to the limit and found a theoretically really interesting result that one can achieve for any fixed D and for any epsilon. One can achieve an almost the best competitive ratio possible. So if alpha star is the best competitive ratio possible, we are able to achieve 1 plus epsilon times alpha stars. And this, more important, can be computing in polynomial time for any fixed D and epsilon. So this is more theoretically interesting that one can achieve this result if it has enough computational resources. Okay, but let's start explaining the first part of the result. So the first part of the result works on all priority-based algorithm. Priority-based algorithm is simply a family of algorithms which assign according to some priority on the machine. So the priority is set according to the current load of the vector of the machine and the arriving vector. Okay, so the algorithm has some disutility function U that depend on the machine state and depend on the next vector, and it just give a number between 0 to infinity. And the algorithm assignment is defined as to assign to the bin which minimize the disutility function. Okay, so you can think about it, the algorithm order the bins according to the load and according to the next vector, and assign to the bin to the first bin in the order. Okay, so first we observe that greedy algorithm can be seen as priority-based algorithm. Its disutility function is just minimize the max span. So if I set the disutility function to be the load after assigning the vector to the bin, I will get exactly the greedy algorithm behavior. Let's see an example. So if the state of the we can see the blue is the state of the Cohen bin, and now the next vector, the red vector, arrives. So I will compare the disutility in assigning it to the left and to the right. So it's easy to see that the max span by assigning to the right is smaller than the max span when I'm assigning to the left, and therefore the greedy algorithm will prefer to assign this vector to the right. Other algorithm that we define according to this priority-based rule is the best fit that don't try to minimize the max span, but just try to balance the two coordinates. I won't get into the exact details, but in the example, you can see that assigning to the left bin will get us more balanced algorithm. So in this case, the priority-based algorithm will prefer to assign it to the left bin. Not that the algorithm need to now opt in advance, because the algorithm checked that we didn't overflow the competitive ratio guarantee alpha. So it need to now opt in advance in order to compute what it's to compare itself to alpha. And last algorithm, this family that we work on is the first fit that assigned to the first being feasible. We can achieve it by just setting a zero for a zero for the machine if we don't overflow the competitive ratio guarantees, and infinity otherwise. Okay, because the priority based algorithm breaks tie consistently, we will get exactly the greedy behavior. Okay, so how to prove for this family of algorithm that's if I want to prove that this priority based is alpha competitive, we need to show, for example, the following. If the average load currently in any dimension is at most 1, and for all machine exerts a coordinate above alpha minus 1, it's close to, then this state is not reachable in alpha. If we are able to show it, then we can say that the algorithm is alpha competitive. Why it is correct? Because if there exists a machine with coordinate above alpha minus 1 and the next vector is 1, 1, then assigning the 1, 1 will overflow the competitive ratio guarantees. And therefore, by ensuring that we don't reach to this state, we know that after all the assignment, we are still alpha competitive. Okay, so we use a binary diagram in order to explain it. So if the average load is at most 1, I would just denote it as VM of 1. Okay, and if for all machine exists a coordinate above alpha minus 1, I denote it as L of alpha. And finally, the C1 is CM is reachable, I denote it, the reachable space, I denote it as RM of alpha. Okay, the only thing that I need to show, so we have 3 sets of configuration, I need to show that this intersection between the 3 sets is empty. By showing it, I will guarantee that the algorithm is indeed alpha competitive. But as I said, analyzing the reachable space of a machine is complicated. So instead, we show that for priority-based algorithm, it's sufficient to analyze the reachable space of just 2 machines, reducing how much the problem is complicated. So in order to show that it's enough to reduce it to 2 machines for d equal 2, we will show 2 observations / lemmas. So first we will show that if we reach to a state, that any subset of 2 machine configuration is reachable if I just focus on the reachable space when I look on 2 machines. And second, I will prove that if the average load is less than 1, then there exists 2 critical being with average load less than 1. Not that I need to extend the definition of average load. So the average load, the regular definition is just if I will multiply by half these 2 coordinates, I will get something but less than 1. But here I extend it to any weighted average. Okay, lambda set me the weighted average, so I can set that if there exists a lambda between 0 to 1, that the average load with this lambda is less than 1, then still the weighted average load is less than 1. And by proving these 2 properties, I will show that we can reduce our problem from m machines to just 2 machines for d equal 2. Okay, but let's start with the first lemma. I need to show that any subset of 2 machine configuration is reachable. And this is quite obvious when I deal with priority-based algorithm. Okay, I need to show that if I reach to this state with a machine, any 2 subset of machine is reachable as well. So ij is reachable in this set, so I need to show that for also if I look at the algorithm on just 2 machines, it is reachable. So how can I show it? So if I look at the last vector assigned to without loss of generality I, so according to priority base, I know it was better to assign it to I rather to assign it to j. But also when I look at just the 2 machine instance, it will be better to assign it to I then to j, so I can just remove this vector and continue by induction, and this obvious observation follows. The second part of the result, I need to show that there are two critical bins with their average load less than 1 if the total average is less than 1. And in order to show it, I will present the load of the machine on the plane. So let's assume that the load of machine I is 0.4 and 1.2. I can represent it as a point on the plane, and I will represent all machine configuration as a point on the plane. So now I will look on the convex hull of this configuration. This define me, and the one thing I know, because the average volume is smaller than 1, then the average point is inside this convex hull. Second, I know that 0, 0 is not inside the convex hull. So if I look at the line connecting Q and 0, 0, I will get to a boundary point of this convex hull. And as you know, each boundary point can be presented as a convex combination of two extreme points, in this case, Ci and Cj. So there exists and exactly as the lemma said, there exists some lambda such that lambda Ci plus 1 minus lambda Cj span this point, and therefore this lemma holds. Okay, so now the question, how can I use? I will show you that it's easy to use these two lemma in order to reduce the dimension of the problem. So we started that with the original sketch of proof. If we reach to a state that in all machine exists a coordinate above alpha minus 1 and the average load is less than 1, then the state is unreachable as using ALG, and this is the Van Noy diagram that shows it. Now, using these 10 lemmas, okay, if I look on this state, I know that there are two critical bins because the load is less than 1. And obviously, these two machine configuration is reachable in R2, and they have, each of them has a coordinate more than alpha minus 1. Okay, so I can just instead of proving on m dimension, it's enough to prove that the intersection between the space of the average load, the weighted average load is less than 1, and exists a coordinate above alpha minus 1 for all machine, and the reachable space of the algorithm is empty. Okay, so we reduce the problem. From a machine to two machines. And now if I go back to how to bound this reachable space of two machines, so one technique is find a covering convex body K, and I just will prove that that the reachable space is contained into K by proving a closure property. In other words, I will prove for any starting point in K and any vector, feasible vector, that means with coordinate less than 1, V. After I will assign V to the configuration Ci Cj using ALG, I will stay in the convex body. And just to give you some closure about the greedy reachable space, I will not get into the details, but we actually found a complete characterization of the greedy reachable space. We found 4 half spaces that define exactly, and using it, we found the exact competitive ratio. And as I said, we did it also for the other algorithm as well. Okay, and one last thing to observe, that we can use this technique for priority-based algorithm and generalize it not just for 2 dimensions, but for any number of dimensions. So this technique, by using standard definition, as we saw, this technique will reduce you a priority-based with 3-dimensional instead of understanding the reachable space of a machine to reachable space just with the machines. Not just you can use also brute force techniques in order to understand what's the competitive ratio, what's the reachable space when the number of dimension is small. Okay, so this is very useful technique that works for any priority-based algorithm. And finally, we took this approach and extended not just to a priority-based algorithm, and showed that using this robust approach, we can achieve almost a near optimal algorithm. So I don't have a lot of time, so I will tell you just a big picture how we did it. So first, we would like to reduce the number of machines, and we found out that one can reduce to the number of machines using the algorithm of one. But for that, we need the number of machines to be large, and we divide it to order of log D machines. And using the algorithm, the previous algorithm, we are able to show that each group will get a amount which is close to its share of the load. That means this algorithm makes sure that each group of machine will get load proportionally to its size. Okay, the second part of the machine, how to assign in each group. So in each group, we compute an optimal decision tree for the big jobs. And we are also able to show how to encapsulate small jobs into pre-allocated bin vectors. Okay, so we use some kind of decision tree in order to assign the big jobs into the small number of jobs. We are able to compute this decision tree because the number of machines is fixed, just order of log D. So there are a lot of interesting technical details, but I leave it to you to read in the full paper. Let me just conclude. So we derive the first non-trivial result for load balancing in 2 dimensions, and our techniques can be generalized to any number of dimensions and a large set of algorithms. So still interesting question is find the optimal priority-based algorithm for D equal 2, 3, also in this case. And so the second part of the result is more theoretically interesting, more theoretically based. We didn't actually compute it. And the question is, there is simple representation of the almost optimal algorithm that we prove that exists one. Thank you very much.